Hello, welcome to the class of high performance computing for scientists and engineers, and we are discussing the module on GPU computing, and today's lecture will be on the topic thread execution in CUDA program, scheduling and memory access. So far we have looked into some basic fundamental aspects of GPU architecture and some important aspects of CUDA programming. What we have understood now is that GPUs are devices with large number of computing cores but with small memory. Especially there is some issues with memory management in the GPUs because these memories are not exactly as similar as the CPU memories, and therefore if we want to execute some job in CPU, couple of things we have to consider, that there are a large number of computing cores in GPU, and we can, if we can use them efficiently, we can get very good speed up compared to the sequential code. However, when looking into this large number of GPU cores, we understand that as there will be parallel execution, the overheads and latency issues can be substantially high. So how can we scale our job so that we can get good performance is an issue, and fortunately we really do not need to write the program for scheduling the tasks for getting right scalability in GPU codes, or especially in CUDA codes. CUDA itself does some scheduling of the threads so that good performance is obtained. However, it is important that we understand that how this scheduling is done. Because there are large number of cores, there are thousands of cores, we understand that now what we are running in a GPU is not running in 8, 16 or 32 processor, but it is running on a very large number of cores, and our idea on parallel computing tells us that as the number of cores will increase, there will be certain issues, latencies, overheads, etc. might come into picture. So you have to be quite careful about while writing GPU program and looking into the performance of the GPU program, that we are getting right scalability, because large number of cores in a sense gives us great flexibility. We can use as many all the cores and we can get very high speed up. However, large number of cores also pose the risk that there can be high overhead, so you have to look into that. The next part is that memory access in GPU is not as simple as CPUs. So you also have to understand that how, when a thread operates, how does it access the memory. If we build some basic understanding on that, we will not indulge ourselves in doing some mistakes which can kill the performance. Again, this I should assert that when we talk about GPU computing, we are using APIs like CUDA. CUDA itself takes care of a lot of the facts. For MPI or for OpenMP, a programmer has to think more in terms of resource allocation, in terms of load balancing, etc. But in case of CUDA, CUDA itself does a lot of the things. However, a programmer must be aware how CUDA is doing that, so that he can be sure of the fact that he is not doing something wrong while writing the program and the performance is not degrading. So, we will look into these aspects. So, what we will look in this lecture and the subsequent lecture is that how the threads are executed in a CUDA program. That also involves scheduling of the threads, which is very important, because as I said, there are thousands of cores. So, more than thousands of threads are there, and how these threads will go to different cores and they which manner they are executed, what is the pattern of their execution, and how the latency is hidden while executing this large number of threads, so that good scalability is obtained. There is something called thread divergence, which is very important for a programmer to understand. We will discuss about thread divergence. It is really a performance killer. If we write a code which is thread divergent, sometime it can go into a deadlock situation also, or sometime it can give us extremely poor performance. Also, we will see about memory access during the kernel execution or thread executions. So, if we look into a CUDA kernel, we can see in a general CUDA program there is a serial code. which is run on the host or on the CPU, then it launches the kernel, and kernel is a function which runs in the device or in the GPU, and when the kernel function is called, it launches a grid. A grid is collection of blocks of threads. So when the grid is launched, many blocks of threads are launched, and each block has a number of threads, and all these threads are operated. After that, the kernel execution part is over, then again control goes to the CPU, it executes the CPU code. I mean, there is an asynchronous way of execution. As soon as the kernels are launched, the CPU can take over and start working on its own, and then again when the parallel part comes, another kernel is launched. The kernel is the function which is executed in GPU. How does it execute it? It is executed in terms of an array of threads. Blocks of threads are launched in terms of a grid. When a kernel is executed, it launches a grid of threads. A grid is collection of blocks, a block is collection of threads. CUDA can launch a large number of threads, and we can see in any practical CUDA program there is granularity in terms of threads, and we can launch hundreds, thousands or 10,000s of threads. A great number of threads can be launched through the kernel. Maximum number of blocks, again block and grid, they are 3-dimensional structures. So a grid can have blocks in all 3 dimensions, a block can have threads in all 3 dimensions. Maximum number of blocks in the x dimension of a grid is 2 to the power 31 minus 1, which is a large number. Again something like 65,000, of the order of 65,000 blocks can be launched in y and z dimension. Now inside each block, so there can be that many number of blocks in a kernel. When a kernel is launched, it can call that many number of blocks. Each block can have large number of threads. So inside each block there can be maximum 1024 threads. These are in the modern GPUs like P100, V100 Tesla series GPUs. So in total we can launch 2 to the power 31 into 60,000 into 60,000 into 1024. That is the maximum number of threads that we can launch. So a large number of threads can actually be launched when a kernel is operated. However, we do not have that many cores. We have very large number of cores. There are 2000, 1000, 2000, 3000 number of cores available in a GPU, but the number of threads that we are launching are mostly much more than the number of cores available. Cores are the units of hardware, units of execution. Each core is like a small arithmetic logical unit and processes the information, crunches the number. There are number of cores, there are thousands of cores in a GPU. However, threads, which a thread will go to a core, but the total number of threads that can be launched can be much more than that, and therefore it becomes important that how do we assign threads to the cores. We have large number of cores, so it's a massively parallel system, but we have much more number of threads. So the program has more granularity and more number of threads or concurrent instruction streams can be devised. So when we launch the kernel, of course more than one threads are launched per core. There are large number of cores but many more number of threads. So each thread also, each core also gets a large number of threads to operate. So how do we schedule the threads? It is important because large number of threads as well as large number of cores can give us all types of problems like latency, like unbalanced load unbalance, like race condition, like cache coherence, etc. So how to schedule these threads rightly into the hardware resource or the cores so that we get good scalability, that is the most important part in thread execution of a CUDA program, and we will look into that. And this scheduling is not something which we are doing. Some of the parameters we can control as a programmer, but mostly done by the hardware and the CUDA API, hardware and compiler. If we revise the GPU architecture. We have earlier looked into GPU architecture. What is a GPU? So, it has a it's a device, it's a graphics card like an accessories attached to the motherboard of a CPU, and it has a there is an interconnect bus which connects through a PCI bus. A GPU is connected to the CPU. Inside GPU we can see the global memory or GPU's device RAM, a constant memory. We will discuss about constant memory, a space for the L2 cache. Modern GPUs have L2 cache. Then something called texture memory, L1 cache or shared memory. We will again discuss about it. And then in the which is connected with the main global memory is many streaming multiprocessors. There are in V100 GPU there are 80 streaming multiprocessors. Inside each streaming multiprocessor there are streaming processors or CUDA cores. So, when a thread is executed, a thread is basically executed on a CUDA core. So, CUDA cores or the streaming processors are part of the streaming multiprocessors. GPU has number of streaming multiprocessors. There are 80 streaming multiprocessors for V100, and streaming multiprocessors, each streaming multiprocessor has number of processors or computing cores or CUDA cores. So, in V100 we can see that 32 dual precision cores are in a streaming multiprocessor. So, total number of cores available are 32 into 80, and each streaming multiprocessor has 32 cores. We are talking about dual precision cores because for most of the scientific engineering purpose, dual precision cores are the important one. And now, if we see how these resources are shared, because there are large number of resources as well as large number of tasks are there among the threads. When a thread operates, this thread runs in a CUDA core. So, as we can launch number of threads when we launch the kernel, each thread goes to one CUDA core. Now, when we and what is a thread? A thread is a member of a block. A thread cannot be launched as its own. A thread is launched as a part of block, and each block goes to one streaming multiprocessor. So, what I am sending as a block of thread, this block is being allotted to or assigned to one streaming multiprocessor. So, if a block has 2000 threads, a maximum is 1024. If a block has 1024 threads, these 1024 threads as a collectively, these 1024 threads go to one streaming multiprocessor. How many cores one streaming multiprocessor has? If we talk about V100, we have just seen it has 80 cores. So, these 80 cores will take care of this 1024 threads. That means, these 1024 threads will be some way scheduled to operate in this 80 cores. We will see how will they. And now 1024 is the max number. There can be less number of threads also, even you can have one thread per block. Well, so a thread will go to a core, the thread block will go to the streaming multiprocessor, and the block also cannot be launched as its own. A block is launched as part of a grid, and the entire grid goes to the GPU. That means it populates over all streaming multiprocessors. A GPU thread runs in a CUDA core. A thread block runs within one streaming multiprocessor. There can be more threads in a block than the number of cores in a streaming multiprocessor. Of course, we talk about launching more threads than total number of cores. Therefore, more threads will be in a block. A thread goes to a block, the number of threads in a block can be more than the number of cores. But also there are 80 streaming multiprocessors available, and we can launch much more larger number of cores, blocks. We have seen that this is 2 to the power 31 minus 1, we can launch in one direction. So, we can launch a large number of blocks. Therefore, there can be more than one blocks assigned to one streaming multiprocessor. One SM can get more than one blocks. And then it is important to schedule the threads as well as schedule the blocks in an SM, so that it can hide the latency, because large number of threads will be there. When these threads are operating, they will have their own latency for memory accessing, for race conditions, for some other purposes. some of the threads will be waiting because some of the threads are not finished. So, how these threads will be scheduled so that this latency can be hidden and we can get reasonably good scalability. Also, it is important to see what is the memory requirement of the block, and especially if we talk about on-chip memory. If we quickly think of the previous slide, each streaming multiprocessor also has some memory, shared memory, which we write some memory unit. So, if we talk about the on-chip memory utility, then what is the memory requirement of the block, how much memory the block requires, that is also an important aspect while scheduling the blocks in the GPU, because if there are more memory, I mean if there are less memory requirement, probably more blocks can be scheduled in together. If there is less memory requirement, then less blocks can, if there are more memory requirement, less blocks can be scheduled. So, what is the memory requirement of the block, and what is the total memory available by in a streaming multiprocessor? In case we look for on-chip memory, that is important. So, when we launch a grid, this is launched by the whole for the whole GPU by the kernel, and also concurrent kernels may run in one GPU, because kernel execution is asynchronous. Once a kernel is launched, goes to a GPU, then the control comes back to the CPU and CPU can do its own work. So, CPU can concurrently place kernels in the GPU. So, so this is also important that different kernels can also be scheduled on the GPU at the same instant. So, this scheduling is a very important part here, and the basic unit of execution in a GPU is warp. Warp is called a group of threads which are scheduled together on a streaming multiprocessor. So, we understand that in a streaming multiprocessor a block will be allotted, all the threads of the block will go to one streaming multiprocessor. Now, say this block has 512 threads. The streaming multiprocessor has 80 cores. So, of course, 512 threads cannot operate on their own. A group of threads will be chosen and they will be first launched into available cores in the streaming multiprocessor. Now, if we take 80 threads, or we are not doing that, CUDA is doing that, CUDA hardware and compiler and the API is doing that. So, if 80 threads are chosen and these 80 threads are put into the streaming multiprocessor, what will happen? That they will do their own work, they will finish their work, then next 80 threads will be taken. Most difficulty that will arise, that instead of getting an advantage of running 512 threads, we are getting a parallelism by the factor 80 only, 80 done, then 80 done, then 80 done, so on. But if we somehow put less number of threads, say less than half of the code threads are less than half of the cores are occupied. As soon as these cores are looking for something like searching for memory, another set of threads can be launched in the free cores, and some of the control will come there, they will operate, they will execute data, and that can give us we've seen that gives us better performance. So, it is not that all the cores of a streaming multiprocessors are active at one instant, but a small number of cores inside the streaming multiprocessors are active and that many threads are chosen, and this unit, the unit combining the number of threads which will go to a streaming multiprocessor as a unit and operate there, is called warp. Number of threads in the warp, what is that number? This number is fixed by the GPU architecture, and this number is essentially 32. So, when a kernel is launched, a block is scheduled in a GPU streaming multiprocessor, and 32 threads among the blocks are first executed in the streaming multiprocessor, and then once they are over, or once they go to latent stage, something like that, another 32 threads are chosen and they are executed together. So, group of 32 threads are combined, and this combinedly taken and they go to the streaming multiprocessor and are executed. So the group of threads that are executed physically in parallel, so these 32 are executing in parallel, is called the basic unit of scheduling, and this is hardware dependent number. This is known as warp. When a GPU works inside its streaming multiprocessor, one warp is activated first, and this is different than block. Block is the total group of threads that are considered as an unit and allocated to a streaming multiprocessor. Number of threads in a block can be different. Number of threads in warp is fixed by the hardware specification or architecture specification. So this is the hardware limit. That means we can see that not all the cores of the GPU are active at one instant. This was taken care of, one of the issue like latency hiding. Another issue is the heating, electricity, power, etc., the other hardware issues. And this number in the modern GPUs, this number is 32. That when a kernel is launched, a block of threads are assigned to a streaming multiprocessor, and among this block 32 threads are chosen, and these 32 threads as a warp is activated in the streaming multiprocessor. 32 cores of the streaming multiprocessor are active at one go, and they are taking up these 32 threads. And then once these 32 threads are launched as an warp, then it can pick up the next warp, next 32 sets of threads, and put it in the free cores of the streaming multiprocessor. And there can be certain overlap. We'll see how these overlaps can be done. There can be some dynamic allocation of the warps inside inside one particular block. And the number of threads in the block is programming specification. Programmer can himself tell that I will take this many number of threads and they will go as a block. Block size can be specified as the programmer, but warp size cannot be specified as the programmer, because this is what is fixed by the architecture of the GPU. So whatever be the block size, 32 threads will be chosen. If you have less than 32 threads in the block, then that less will be chosen, but if you have more than 32 threads, 32 will be chosen and they will be active. That means 32 cores of the streaming multiprocessors are active and they will pick up threads. In case you have less threads in the block, then few of the cores will be inactive, you will lose in terms of performance. So that is also important to see. In case you have threads which are not in case the block size, number of threads in a block is not multiple of 32, say you have 59 block threads in a block, so 32 will go first and the remaining 27 will go in as the next warp, so 5 will be inactive. You will lose in terms of performance because you are also running many blocks. The next block will come and that will also lose in terms of performance because some of the cores will be idle. So that means when a GPU program runs inside each streaming multiprocessor, the streaming multiprocessors also work parallelly, but one block goes to one streaming multiprocessor, and inside one streaming multiprocessor only 32 are chosen and active at one point of time, and then the next 32 will be chosen, and that's how they are scheduled. So if the number of streaming multiprocessors, because one block goes to one streaming multiprocessor, if your block number is less than the number of streaming multiprocessor, you are losing also, because some of the streaming multiprocessors are inactive. Also, if your block size is less than the warp size, then you are losing because some of the cores are inactive. These are two very important aspects. Groups of threads within the same block are launched as sets of warps in a particular streaming multiprocessor. So say if two blocks are assigned to one streaming multiprocessor and each of the blocks have 16 threads, these 16 threads of two different blocks cannot be chosen as part of the same warp. A warp, what is chosen in the warp, these are the threads within the same block. So there will be first 16 activated and then the next 16 will come as the next warp. So they cannot be, threads cannot be picked up from different blocks and mixed with another block's thread and put into the same warp. That cannot be done. Warp is always restricted to a particular block. well. So, this gives us certain idea about scheduling in GPUs, and this will be required later for understanding it better. Now, how the works are executed. Streaming multiprocessor creates, manages, schedules and executes threads at warp level granularity. So, at one go, one warp is executed. Each warp consists 32 threads of contiguous thread IDs. So, they cannot be chosen randomly from thread ID 1 to thread ID 32 or thread ID 0 to thread ID 31, sorry, it starts from 0 will be one warp, thread ID 32 to 63 will be another warp, so on. All threads in a warp executes the same instruction. There cannot be different instructions for different threads. All threads will execute same instruction following a single instruction multiple data or single instruction multiple thread model. At this level, essentially a vector processor level architecture works, that it takes data from same it is mostly desired that it should take data from contiguous memory location. It takes data from the same location, different memory elements, and operates does the same operations over them. If the threads of the warp diverge on execution branch, each branch is serially executed serially, adding latency. This particular part, divergence of the execution path, we will see in a while, we will see in detail, but this basically means that some of the threads inside a warp is scheduled to do something else, the other threads are scheduled to do something else. How will you do that? You will do it using some if else condition. If thread IDs are this, they will do operation A, if otherwise they will do operation B. If it is done, it is seen that while operation A has been executed, the other threads who are not supposed to do operation B, they are sitting idle, that they are going into latent stage. These cores will be sitting idle. So, there will be some sequentiality among different operations. If the warp is given two different operations, they will be followed sequentially, it cannot be done parallelly. So, whatever is given in the warp, that they will, all the cores will do essentially same work. If you ask them to do multiple work using some if else statement, that will be done serially and that will add to latency. When a warp executes an instruction that accesses the global memory, in the ideal case it coalesces the memory access of the threads and the within the warp to make as few as transactions as possible. So, when the warp talks to the global memory, it is desired that it reads from the global memory in a coalesced manner, a contiguous data from the global memory and written in a, because threads within a warp are identified by contiguous thread IDs. Similarly, the memory location must be contiguous and memory must be coalesced. Instead of 2D arrays, it should be a 1D array as much as possible, so that they can read one by one, the threads can read the memory one by one, or as the threads will go, they can take a contiguous piece of memory and pull it to the register and operate accordingly. So, that is the desired thing, and if you can make the memory coalesced and contiguous, you will get better performance. Now, how this warps are scheduled within a block, and this is extremely important. Once the thread block is launched in the multiprocessor, all of its works are resident until their execution is finished. So, once a thread block is associated to the multiprocessor, all of the warps we consider that they are residing in the multiprocessor. So, what happens to the residing threads, residing warps? The threads becomes a resident, threads becomes allotted to the multiprocessor and they are residing, staying there. Therefore, each of these threads get one register. Some register, one or few, some register memories are assigned to the variables given to the threads, and these register memories are on-chip memories, which are in the attached to the streaming multiprocessor. They can be very fast read. In case the threads require more memory than the register memory, it has to be allocated as local memory, and it comes from the global memory, and it becomes a slower process. But mostly we will try to ensure that is important of finding out what will be the number of blocks, number of threads, etc., that the threads get enough register. And interestingly, GPUs have very large number of registers. A streaming multiprocessor in GPU has very large number of registers. So, whatever are the memory requirement, that comes from the register memory itself. Well, within the block, warps are scheduled for best performance. How do these warps operate? They will operate. See, within a block there is not only one warp. One warp is scheduled first, it goes in operation, but later next warps will come. Warp has 32 core threads, that means 32 cores will be populated by this warp. However, streaming multiprocessor has say 80 V100 has 80 cores, therefore another warp can also be active, and this scheduling is done for best performance. How? That is that consider a warp of 32 threads executing an instruction. If some of the operands are not ready and fetching memory from RAM, say I have to read an array, some of the threads will read from an array which is in the main device time. This reading is slow. The streaming multiprocessor says that this, so what happens, the threads which are supposed to look into that memory, the threads which are supposed to look into that there are threads which are part of the warp. These threads now are not doing any processing on the GPU. These threads are looking from memory, they are reading memory from the device time. It takes some time. What does the streaming multiprocessor do? It puts these threads into a latent stage, it hides the threads, it launches the next warp which will do some operation. By the time this memory fetching is done by the threads, that time another warp is launched, and this process is called context switching, that instead of working on this particular warp, streaming multiprocessor started working on another warp, and that is why warp size is much smaller than the number of cores in different perspectives. One perspective is that it can do the context switching. How is this context switching is done? That the threads in these warps have their own register memory. Streaming multiprocessor has large number of registers, and other registers are associated with the next warp, and then this next warp starts operating. Now once next warp does some memory search, by that time this particular warp which was launched first has got its memory and loaded the registers. It is become active again, and there is a switching away from the warps, but the register data always remain on the warps. Register of a particular thread, once a thread is resident, its register is active. So as soon as it is ready, its registers are populated from the device time memory. The other thread which is searching for other warp, which threads are searching from memory, goes into background and comes into the previous warp, and it is activated. In this way, a number of warps can concurrently work, hiding their latency. Once one is looking for memory, the other warp will be active and it will search for the memory. And through this process, the GPUs hide their thread level latency and show improved scalability. GPUs have large number of register files for context switching, and therefore they have scalable scheduling. So this is the way by which warp has only 32 threads, but actually you get a parallel performance which is more than 32 threads, because some of the latency of these 32 threads in terms of memory fetching and or some other activities is hidden by activation of the next warp, and this is done by using large number of register files. So few of the important programming aspects what we understand from the behavior of the pattern of the execution of the threads. Number of threads in a block or the block size should be multiple of warp size for write scalability, because it is warps which will be activated as a group of threads at one go. So if your block size is not we have discussed it earlier, not a multiple of warp size or less than the warp size, some of the cores will be inactive, some of the cores will be idle, and you will get worse performance. And this can be done, that what is the optimum block size, a question comes here. This is also considering that how much memory utility has been done, because there is memory fetching. So as one warp looks for the memory, in ideal case, for example, say there is no context switching inside a streaming multiprocessor, then one warp is good enough as the size, one warp as the block size, one warp is active, done. But once one warp will be finished, then next warp will be taken. But now as context switching is there, so how much memory they are searching for, or if they are using shared memory or on chip memory, how much memory is being used, that is also another part. So depending on that, we can see that optimum block size is a multiple of warp size, but how much is this, that has to be that depends on the programs and execution, etc. But it is seen that maximum number of blocks is 1024, but for large problems we can see that 512 block size in case of a BiCG step solver gives us best performance. So something like 256, 512 multiples of the warp size gives us better performance. And thread divergence has to be avoided, and this is a very important issue. We will look into it later, that threads within a block must not take different execution path. They should, all the threads should do same work, there should not be branching of work among the threads, because again it is a warp which is being activated. So the warp will do, all the threads in the warp will finish their job. If there are multiple jobs, if the different threads in the warp are supposed to do different things, there will be certain issues, some sequentiality, and it will kill the performance. We will look into thread divergence in detail and also look about memory issues in the next class. Thank you.